Okay, today we want to talk about compositions of functions. This is where you take some input and you plug it into one function, you get an answer, and then you plug it into another function and you get an answer. Shouldn't be a new concept, but we're really going to try to focus a lot on try to find in the domain of these new functions, which can be a little bit, it's a process, right? Once we learn how to do it, it's not so bad. The way that this is written, a lot of times you'll see is f of g of x, which I really don't like that notation. That's not the letter O, and it's not a times symbol. It's just a little circle halfway through the line. If you see on your packets here, it looks like that. You also might see it written as f of g of x, or maybe just f of g is the composition. But remember what this means is, the way I like to think of it always is f of g of x. Using the double parentheses, I think, really points out that x is going to go into g first, right? We're going to evaluate that, then we're going to take that and put it in f. These are all equivalent, right? They're all equivalent. And again, you might even see it written as, I really don't like not including the input variable, but you also might see it like that. It's not fog, right, or golf. It's an operator. So we read it f of g, or f of g of x, f of g of x, or this would be f of g of x also. So that's just our notation there. So for our first example, we have if f of x is equal to x squared and g of x is equal to 2x minus 1, just find a couple quick ones here. So if we wanted to find f of g of 5, that's your first example there. So what we're going to do here, we're going to take 5, plug it into g, evaluate it, take that answer, plug it into f, and evaluate it. It's really important to note, though, we just did combinations last class. This is not multiplication, right? If you multiplied the two functions together, you would get a new function, but it would be different than the composition. Right? That's a combination. This is a composition. The words are close, but they mean different things. It's really important to keep those straight. So here, again, I would like to think of this as f of g of 5. And so now this tells us I'm working from the inside out. I'm going to take the rule called G, which says take the input, so 2 times the input minus 1. So this will be f 2 times the input minus 1. Write this out, really reinforce the skill. Always when you substitute, I'd recommend that you put a parenthesis around it to remind you of distributed negatives or different things. So that's going to be 10 minus 1, so that's f of 9. Now at this point, we'll take this. The function for f of x tells us to take the input and square it. So that will give us 9 squared, which will give us 81. Why don't you go ahead now and find these next two. We had g of f of 7, and then we have f of 3. Now in this case, we're going to plug it into 3, get the answer. I'm sorry, plug 3 into f, get the answer, and then plug it back in. It's like you do it twice. Okay? Take a couple minutes and try those. So as we evaluate this is g of f of 7. You have to do it in order. Order almost always matters with compositions, just like subtraction or division. Right? It matters. So here, what this is going to be, and write this step, g is farthest from the 7, so g of f of 7. Okay? If you're missing it and you're not showing all these steps, then you need to show all these steps. Right? If you're getting them all right, you're getting them all right. That's great. But if you're not, you should really write this out. So the first thing I do is f of 7. The rule for f of x tells us take the input and square it. So I'm going to remove the x, and I'm going to put a 7 in there. So the g is still just hanging around outside, and then we're going to get 7 squared. Right? So we're just squaring 7. So then we're going to get g of 49. I haven't done anything with g yet because I'm trying to get that inner piece simplified here. So then we're going to take g of 49. G of x tells us 2 times the input minus 1. Okay. So that's going to be 2 times 49 minus 1, and that's going to be 94. 7. Okay. Lastly, we have f of 3. So again, I like to write it like that, if that helps you. Some people will do f of 3 off to the side and then plug it in. You just got to find what works for you, but you want to be able to keep the correct statement all the way kind of as you work there. So here we're going to get f tells us to take the number and cube it. So we're going to get f of 3 squared, right, which is 9. Okay, now f again tells us take the input and square it. So we get 9 squared, and that gives us 81. So make sure that you're able to work through that entire process. Okay, so we just looked at plugging numbers in, right? Which is fine. We should be able to do that, right? You put it in one, you get an answer. You put it in the other, you get the final answer. But a lot of times, maybe you want to do a graph of this, or maybe you want to do for 50 different points. It's a lot quicker to just write one new function that'll do the work of the 2 old functions. You don't actually have to do the composition. So with that, we can write rules like this as f of g of x. Okay, x is just going to be some input. Right? It's just a placeholder. You might hear it called a dummy variable, right? It's just holding the place for us. So with this one, we'll do the same process. We'll get f of g of x. Again, I just rewrote it, right? Whatever's furthest from the x comes last. Whatever's closest comes first. If you switch the order, that's a detail we have to pay attention to. You can't do that. So now to evaluate this, g of x is equivalent to 2x minus 1. So I'm going to remove the g of x, and I'm going to replace it with 2x minus 1. F is still there, but now it's f of 2x minus 1. So I need to take the function f, and the new input is going to be 2x minus 1. Okay, so with that, the rule for f says take the input, which is x, that's the dummy variable, and square it. So I'm going to take the input in the parenthesis, and I'm going to square it. So that'll give us 2x minus 1 squared, which is probably fine. We should be able to square it, right? Whether you write 2 parentheses out or whether you use your binomial squared, probably the best answer is 4x squared minus 4x plus 1. But that would be f of g of x. This would be a new rule. Okay. Now, what I want to point out real quick is on the last, when we did numbers, we did, where can I do this? I can just erase this for a second. But I want you to note here, this was the problem there. But if I do f of g of 5, which we did earlier, right? We just did. But I could use this rule, and I'm going to get the same answer. Okay. So if I use that rule, because we have a new function, f of g of x, I could say 4 times 5 squared minus 4 times 5 plus 1, right? Because this rule tells us 4 times the input squared minus 4 times the input plus 1. So we do that, we get 100, take away 20, add 1, and we get 81, which was the same answer we just had. Okay? So I'd like you to go ahead then and find the next two, which were g of f of x and f of x. So we want to do g of f of x and then f of x. And we'll look at those. Okay, so for g of f of x, this is normally going to be different than f of g of x. It's kind of a special case if they're the same. We'll see some of those. But so again, this is equivalent to g of f of x. So again, I'm going to remove f of x, and I'm going to replace it with x squared. We do that. Now, the rule for g says 2 times the input minus x. Really important, we're removing this x. We're replacing it with an x squared. Seems a little weird, right, that you're same letter, but it's just how we do it. So we're going to get 2x squared plus 1, right? 2 times the input plus 1. Probably make this look a little nicer, would be 2x squared plus 1. Okay. If you check the last one, I think it was 97 when we did g of f of 7. If you put 7 in there, you get 49 times 2 minus 1, what I do, it was minus 1. I just wrote the wrong rule down. But you get 97 again. So here's f of x. Looks scary, actually goes pretty quickly here. Right, f of x, so the inner f of x is x squared. And notice when you use the function, you stop writing that letter. Right, it's like you're cashing in an f of x for an x squared. And now f tells us again to square the input. The input is x squared. We square it, and that gives us x to the 4th. There we go. Okay, for example 2, we have 2 new functions, right? And you'll need to have them identified each time. F of x equals 3x plus 8. G of x equals x squared, right? Input squared, 3 times the input plus 8. If we're going to find g of f of x, again, I like to think of that as g of f of x. Right? If it seems like a waste of time to write that step, it might be, but if it helps keep you organized and makes it easier for you to do it, it's definitely worthwhile. And then we're going to get g of 3x plus 8, right? I pulled out the f of x and replaced it with 3x plus 8. It's an equation. That's what we can do. Just substitute there. The rule for g says to square it. Is that right? Okay, so there we get 3x plus 8 squared. If you don't know your binomial squared pattern, which probably some of us don't, then you need to write 3x plus 8, 3x plus 8, and then multiply that out. Right? So to do that, 9x squared plus 24x plus 24x plus 64, and that would give us 9x squared plus 48x plus 64. Okay. And you could also be argued this was a pretty good answer right here too. Like sometimes you could just leave it like that. It just sort of depends what we're doing with it, right? This is not a bad rule. This is actually much easier to plug numbers into this and evaluate than it is to plug numbers into here, just because there's fewer terms. Okay, so either one of these would be fine. This one and that one, and that's a lot easier to get to, so I'd probably leave it. So now we have f of x. So f of x, we'll take the inner f of x and replace it with 3x plus 8. Well, now the rule for f of x, this gets a little weird sometimes when you plug it into itself. I think people tend to get tricked by this a bit. But just really try to describe what the function is doing. 3 times the input, then add 8. So this is the input, right? So 3 times the input would be 3 times the input plus 8. Right? So if you look, what I put in this parenthesis just took the place of x up here in this original rule. And that's going to give us 9x plus 24 plus 8. And that's 9x plus 32. That's how we do that. Okay, for example 3, we have if f of x is x squared and g of x is equal to x, the square root of x minus 3. So in order to find this, we'll do f of g of x. So g comes first. So we'll get f of the square root of x minus 3. Right? And then f tells us to square whatever's in there, so we'll get the square root of x minus 3 squared, which we all know is x minus 3. Right? Now here's kind of the catch here. This is what we have to investigate here, and we'll probably come back to this problem potentially, is with this, if you just use this new rule, right, and say I want to do f of g of 0, right? Well, I'd do 0 minus 3, my answer would be negative 3, wouldn't it? But if we did it as a composition, the actual two-step process, if you plug 0 into g, what do you get? The square root of negative 3. That's not a real number. Like, we're keeping it real for now. We're not doing imaginary numbers today. Okay, so it would fail right away, correct? Even though this looks like there's going to be an answer of negative 3, if you do it step by step, you'll see that it fails if you put 0 in here. So we're going to have to investigate that, and that's what we're looking at here. So we'll come back to that in a second. Here we have g of f of x. So that's going to be g of x squared. Right. Then we're going to take this rule, we're going to pull this x out, replace it with x squared. So we get the square root of x squared minus 3. Now this one, we can see there's probably some domain issues here, correct? Like for instance, again, if I put 0 in here, it's going to be undefined. Or if I put 1 in here, it's going to be undefined. So we can talk about how to find the domain of that. But we'll come back to this in just a second. What I want to look at now is on the bottom of your worksheet is we have this information which talks about the compositions of functions and how we define the domain of them, right? What x's are going to actually produce an answer. So for this, and this is the bottom there, it says the domain of f of g of x is defined when both, now this is important to note this. If I write f of g of x, g comes first, correct? And then f comes second. So if I look at that, is defined when both g of x, the first function, and f of g of x, which is the final answer, are defined. So we have to look two places. If there's a domain restriction in the first function, we have to respect it. And if there's a domain restriction in the final answer, we have to respect it. Example 3 that we just looked at, I think on the left we had f of g of x. It had a problem with the initial function. And the g of f of x had a problem with the final function. So we look at that way. So again, to find the domain of the, what we do is we find the domain of g of x. That's the first function. Right? Then we find the domain of f of g of x, which is the final answer. The domain of the composition is the overlap, or the intersection of those two. We talked about intersections yesterday. Right? So if it's a problem in the first function, or it's a problem in the final answer, it's not part of the domain. If it works in the first and it works in the final answer, it's part of the domain. Okay, so I'll put this over here. If we go back now to the example 3 that we just looked at, here we did f of g of x, correct? So it's always nice when you're looking at these, what I tend to try to do is I look, this domain here for f of x is all reals, correct? There's no problems there, it's x squared. So I just kind of note these. Over here, we get x is greater than or equal to 3, would be our domain. Yep. So as I look, the first function we did here was this, which has a domain restriction, correct? That x has to be greater than or equal to 3. The final answer, does that have any problems? No. So we have to include the domain with that to make it a good answer. So we would say that f of g of x equals x minus 3 given that x is greater than or equal to 3. That's actually, we actually want to include the domain after the function, just like a piecewise function. Right? That's what we're doing. We're saying this is the rule as long as x is greater than or equal to 3. Right? If there's no rule written for less than 3, then it's just undefined. Right? Or you could also say the domain, if you wanted to, you could say it goes from 3 to infinity. Now this next one over here, for this one, if we look at it, the first function is x squared. We're all good, right? You can do anything you want. This one, that's kind of an issue, correct? And this is something we have not talked a ton about, but we know from our work with domain that x squared minus 3 must be greater than or equal to 0. Okay? With inequalities, there's a couple of differences from equations. One is if you multiply or divide by a negative, you have to reverse the inequality. But the other one is if you do quadratics, you can't really do them the way we want to do them. You can't just solve for x squared because we don't know which way the inequality will face. So what we do is we make what's called a sign table. This is as good a time as any to look at it. What you'll do is you'll get this where 0's on one side, which we have. Okay? And then we'll want to calculate when the left-hand side is equal to 0. Right? When is it actually going to be equal to 0? Okay. And this idea we'll use for this. For these quadratic inequalities, we'll use it when we're graphing rational functions, polynomial functions, a whole lot of uses. So to do this, we get x squared equals 3, and then x equals plus or minus the square root of 3. Don't forget your plus or minus. Okay, so these are the zeros. So the first thing we do is we find the zeros. Now, if I think of a number line, that would be at negative radical 3 and positive radical 3. Right, those are the zeros of the function. Now, you might know, what kind of graph is this? It's quadratic, right? A parabola that opens up. Does it make sense that it would, if this is the x-axis, it would look kind of like that? Okay, so if you know that, you might not have to do this whole process. But what we're going to make is a little sine table. So we look at this. Would radical 3 and negative radical 3 actually solve this inequality? Because you'd get 0 is greater than or equal to 0. That's good, right? That's a solution. That's a true statement. 0 is equal to itself. So I'm going to go ahead and put closed circles here to remind myself that those two numbers will be part of the solution set. What we want to do now is take the number line, or the x-axis, however you want to think of it, and we'll divide it into intervals. And then radical 3 to infinity. What we're going to find is if you think of a function, it can only cross the x-axis through a 0. Right? It can't just like stop and jump over and do something. It doesn't do that unless there's an asymptote, which there's not. So for each of these intervals, so first we'll list our intervals, and then we're going to list our test value. I can pick any number I want between negative infinity and negative radical 3. Just don't pick negative radical 3. A good number would be negative 3. Does that seem reasonable? Negative 3 is a good number. Okay. Here, between negative radical 3 and radical 3, I always pick 0 if I get the chance because it makes my life easier, makes the math easier. Over here, I can pick positive 3. Just make sure you're picking them from those intervals. Okay. What we do now is we look back at, we test it in this actual function here. Okay, we're going to test it. So that was our test point. And then we're going to plug it into x squared minus 3. I don't care what answer it gives me. All I care is if the answer is positive or negative, which really makes it easy. You don't have to calculate stuff. But if we do negative 3 and square it, we know we get 9. Take away 3, we get 6, which is positive. Here, if you put 0 in here, you get 0 minus 3, which is negative. Right. And then here, we get 9 minus 3, which is positive. Did we want x squared minus 3 to be greater than 0 or less than 0? We want it to be greater than or equal to 0. So that tells us that these two intervals, where it's positive, that's going to be the domain of our function. Meaning, for this, we would say that our domain is that x is contained from negative infinity to negative radical 3 and radical 3 to infinity. That would, now, you might be thinking, well, I don't believe that. That seems dumb. Which maybe you could think that. But if you could kind of test, like, so if this is our domain, should negative 10 give us an answer? Sure, if you put this in here, that would give you 100 minus 3, which that's positive, we can square root it, right? Would 6 give us an answer? Sure. But would 1 give us an answer, which is out of this, right? No, it fails, right? And you might notice that if you put these endpoints in, you'd get the square root of 0. Okay, and again, you can compare that to the idea that the graph of this would look like, not of this, but of y equals x squared minus 3, which was the underneath the square root. You want to know where it's above, right? And that's what we have found there. So that's that whole process. That's kind of a big one. But that's something we're going to do more with. Right? We're not going to get super caught up with it now, but I just want to take this chance to show it to you because it's kind of important technique. Okay, so here look at example 4. If h of x equals x squared, m of x equals radical x, find h of m of x. You'll get in that, you want to get in the habit of really every time you look at a function, if I see a square root, I'm thinking there's a domain restriction, right? I know right away, you can tell what the domain restriction is as you take whatever's under the radical and you say it's greater than or equal to 0. Okay. This one, x squared, I can do anything, so I say my domain's all reals. But you really want to get good at spotting domain restrictions. Or either when you got division by x, or something with x in it, or you have that square root. So with this one, we're going to do, again, this is the same as h of m of x. I'm going to replace m of x with the square root of x. First function had a restriction, carries through to the final answer. And then I'm going to do h, which says take the input and square it, which is just x, correct? All the trouble went away when you squared a square root. You're back to the original. But we need to put the restriction x is greater than or equal to 0. Okay? You have to put that greater than or equal to 0, or else it won't be right. That's h of m of x. Because right below this, it asks us to find h of m of 16 and then h of m of negative 100. If we did not include the domain restriction, right, if we just had written h of m of x equals x, then when you did h of m of 16, well, it doesn't matter. It's in the domain, correct? 16 is greater than or equal to 0. So you plug in x, you get x as your answer. So it equals 16. For h of m of negative 100, well, if you didn't have this here, you'd think the answer was negative 100. But you'd be wrong, right? Because if you did the two-step process, it would fail right away because you can't take the square root of a negative. So because we have this domain restriction, we can just say that this is undefined, is what happens there. Okay, so with this, and it's kind of interesting if you want to look at it. If you did m of h of x, it has no domain issues. It's all reals, right? Because the first function's fine and the final answer's fine. Okay, our next problem here is a triple composition. We have f of g of h of x. So again, we start from x, we work our way out. So this is the same as writing f, parenthesis g, parenthesis h, parenthesis x, and then make sure you have the same number of left-hand and right-hand parentheses. So our first step here, it did ask on this question to try to think about the domain. Let's just see what's going to happen with the domain, see if we can figure this out. So for h of x is the rule x minus 1. No domain problems there, we're all good. So we get f of g of x minus 1. Again, we're just working our way out. So g tells you to square root the input. Right, so the input is x minus 1. So we get f of the square root of x minus 1. Now that would have a domain restriction, correct? So since it's showing up here as one of these functions, I think we need to respect it, but we're going to check to see if we needed to. We can check that pretty easily. And then lastly, f tells us to take the input, square it, subtract 1, x minus 1 is x minus 2. So if we look at this, there's no domain restriction in the final answer. There's no domain restriction in the first function. The question is, does this domain restriction matter? Okay, so if I look at that one, like if we're looking at this function here, this would be x minus 1 must be greater than or equal to 0, correct? Even though it's the original, I'm not so worried about right now. But this would give us that x is greater than or equal to 1, would be the implication. So let's take a number that's out of this domain and run it through the three-step process and see if it works, right? So let's think about 0 is less than 1. It's my favorite number, 0. So what's h of 0? That would be negative 1. Then if you plug that into g, you get the square root of negative 1, which would fail, right? Doesn't work. Let's see if 1 would work. So I put 1 in here for h, and I get 0. Can I square root 0? Sure, 1 works. You could try 2 just to see, but if you put 2 in here, This is our first function. You get 1, and we're able to square root 1. So it ends up, this domain restriction does carry through to the end if it pops up in the second function. So we'd say where x is greater than or equal to 1 would be our answer for f of g of h of x. Again, the domain's kind of tricky there. That feels kind of extra credit type tricky stuff. More than. Okay, the last thing we want to do is identify how to make a complicated function into 2 or more simple functions. Okay, so for this, identify a composition of 2 functions such that capital F of x is equal to f of g of x. I should put x's on both sides. Now, in math, in algebra, calculus, capital F and lowercase f just represent different things. They're just different. Like they're not the same. Even though it's the same letter, they mean different things. They might be related. That's usually why you use them. So here, what it's saying is we have some complicated function like capital F of x. We want to find what's little g of x and little f of x in this form so that we could do a composition. We're working backwards. We want to find the basic functions to make this complicated function. It's really pretty nice. I think it's a pretty simple process most of the time. So here we're doing g first, correct? Because it's close to the x, and then we do f. All you want to do on these is look at the function and ask, if I were to plug a number in, if I were to put a number in for x, what's the first thing that I would do to that number? Well, I hope you'd add 9, right? So, what's a rule that says take the input and add 9? What's that look like? It's just x plus 9, right? Now, once I take that input and I add 9 to it, what do I do next? I take the 4th root, correct? So, to write a function that says take the input and do the 4th root, it would be g of x equals the 4th root of x. That's it. So you could check it by doing g of f, or f of g of x. Did I do it backwards? I sure did do it backwards, didn't I? Let's start over there. G was the first one, right? I was out of order. G is the first one. So g of x would be x plus 9. Sorry about that. And then f of x would be the 4th root of x. Now, I was going to check it, and it was going to fail miserably. So it would have worked out okay. But you be careful. So then to check it, f of g of x would be f of x plus 9. And then this f says take the input, take the 4th root. And there we go. Checks out. It's the same thing. So go ahead and try this next one here. And you can try the rest of them on this page. We'll look at them. All right, so our next one here, we have capital F of x, right? The complicated function is the quantity x minus 2 squared. So if we imagine plugging in a number, the first thing we do, which we're going to call g of x, do it right this time, is we're going to do the input minus 2. So g of x would be x minus 2. I'm not sure why I put a parenthesis there. Doesn't hurt, but not really necessary. And the next thing we're going to do is you're going to take, if you had an input here, you'd subtract 2 from it, then you'd square it, correct? So f of x will just be the squaring function. So f of x equals x squared. That's how that works. It's nice. There's only 2 operations, so there's kind of always one right answer. Sometimes you might be able to do it different ways as things get more complicated. Our next one here, we're asked to write f of x as a composition of 3 functions, f of g of h of x. So again, h of x is going to come first, then g of x, then f of x. So imagine we're plugging in a number for x. The first thing we do is we square it, right? Okay, then you add 1. Then you do 1 divided by the input, which could be the reciprocal function. So this would be h of x would be x squared. G of x would be x plus 1. Now, again, the first function dealt with the x squared, so here we just put x plus 1. Right? And then you want to take 1 divided by the input, so f of x would be 1 over x. Sometimes you may see that written as x to the negative 1 power, just to kind of compare there. So there's one more on here if you want to go ahead and try that one, and then we'll be done for the day. So it is, it's going to be a triple composition, and you're given that f of x equals 4 plus radical x to the 9th power. We want to write it in the form f of g of h of x. So for our last one, right, the first thing we're going to do, we can see is that x is being square rooted. So our first function we call an h in this model. So h of x would just be the square root function. Again, remember, x is just a dummy variable. Whatever you're plugging in, we're square rooting it. The next thing we would do is add 4. Or you could say 4 plus whatever you're putting in if you wanted to. Doesn't matter, but g of x, I'm going to write it as 4 plus x. And then the last thing we do is we take the input, again, this would be the x, the dummy variable part, and we take the 9th, or take it to the 9th power. So f of x would be x to the 9th. Okay, and again, you could check any of these, right? These are really easy to check. The nice thing is, too, you don't have to, when you're doing these, you don't really have to worry about domain as much. It kind of takes care of itself later on. So as you're working through things tonight, just make sure to consider the domain.